Our next talk is by John Spray, and it's about using Ceph to provide scalable storage for OpenNebula. Have fun.
Thank you. So many of you will be familiar with Ceph. Quick show of hands. Who is familiar with Ceph? Okay, pretty much everyone. Who has ever installed Ceph? Okay, and who is using Ceph in production today? Just a couple of people. Okay, that's a pretty normal ratio. Right, got that back on. So I'll briefly introduce what Ceph is for those who haven't come across it at all. I'll go into some detail about the Ceph architecture so that those of you who are familiar with Ceph can get a better idea of how it works internally. I'll talk about how you can use Ceph with OpenNebula, and then I'll give a little update on what's been happening with Ceph recently and what's new. So Ceph is a highly available, resilient, distributed object store. What that means is it gives you a place to put data across a population of commodity servers and hard drives. It's free software, it's LGPL, it's available under a similar model to a lot of other free software in that you can download it and use it, but there are also several companies that can provide support for it if you need that. Ceph is actually a surprisingly old project. It started life a little over 10 years ago. We recently had 10-year t-shirts made. They're quite cool. And one of the special things about Ceph is that it's very flexible in that you can use it as a block store, as an object store, as a block device, and you can also use it as a POSIX file system. And the place that you see it most often is used as a store for virtual machine images within private clouds, such as OpenNebula. And so that represents the variety of ways that you can access it. The object store that we provide, the Rados gateway, or RGW, provides an S3 compatible interface or a Swift compatible interface. So that's a very useful thing if you want to be interoperable between other clouds. The RBD block device, the Rados block device, is a fairly full-featured shared storage block device. Similar products are often referred to as server SANs or vSAN type things. We don't generally call it that, but it's comparable. And the file system that we provide is POSIX compliant, so it's better than NFS in that way, and it's comparable to things like GlusterFS and Lustre. So all three of those components sit on top of the layer that we call Rados, which is an acronym for Reliable Autonomous Distributed Object Store. Got it right. LibRados is the software layer that allows a client access to Rados, and Rados itself consists of a large number of object storage daemons. These are Linux processes, one per hard drive, in effect, and they sit on top of a local file system, which is usually XFS, but one can select a different one there. And all of those OSDs together, on the right-hand side, form a cluster. And you can see there are some M's in there, along with the OSDs. So there are actually two types of service here. The OSDs store the data, and the monitors provide the management and configuration for the system. So when a client wants to talk to a Rados cluster, it talks to the monitors, and the monitors tell it where the OSDs are. But no data flows through the monitors. That happens in a purely scale-out way across the OSDs. And from the application's point of view, the Rados cluster is opaque. It talks to this red box, and only within that red box is there this division of the data between the OSDs, so that's hidden from an application. The challenge in designing a distributed storage system is deciding where to put the data. So given an object with a name, how do you decide from 100 hard drives which one to put it on? And when you want to read that object back by its name, how do you remember where it was? One option here is to have a metadata server, which records for each object where it was put, so that when you want to read it back, you can go and look at the metadata server and get it. That is a classic scaling bottleneck in a distributed storage system, and it's something that you really want to avoid if you want to be a truly scale-out system. Calculated placement works a lot better, so you can do something like calculating the hash of an object's name, and using that hash modulo your number of OSDs, work out where to get it. And you can do that repeatedly so that you can go and read it back from the same place you wrote it. The trouble with that is if I was dividing up my object space and putting A to G in this particular place at the top, what would I do if one of these OSDs in the top area became unavailable? How would I make a decision about where else I could put it? So we need something a little bit better than that, and this is an algorithm called crush. With the crush algorithm, we split up our data into uniquely named objects, where each of these colors is a different object. And we scatter them across the OSDs. And I'm not going to explain exactly how crush works, because it's a somewhat complex algorithm, but take my word for it, it works very well. And it also gives us multiple locations for each object so that we can do replication. You'll notice that, for example, the yellow block there is present both at the top right and at the bottom right. And so that gives us the ability to do our resilience in our storage so that if we lose an OSD, we're still okay. And importantly, this is actually a fairly quick calculation computationally, which means we can do it every time we read an object and every time we write an object. So we don't have to remember anything at all. We just need the name of an object, and that allows us to go get it. It has some other nice properties, such as efficient rebalancing of data when something is lost. So if you use a more naive approach, such as a sort of ring-based system, where you just use the hash of an object to pick from a range, if some range becomes unavailable, you might have to shuffle a lot of data around in order to rebalance your system, whereas Crush allows us to move more or less the minimum amount of data necessary, so that when we lose a system, we don't use too much bandwidth re-replicating the data. So that was a very brief overview of how the bottom part, the red part, Rados, works. The part that we're most interested in for OpenNebula, of the three across the top, is RBD, the block device. So let's go into that in a little bit more detail. RBD allows us to take an arbitrarily large virtual drive and map each location in that disk image to objects within the underlying Rados store. So we essentially take the offset within the image, find which 4 megabyte, that's customizable, but 4 megabyte by default chunk it's in, and that chunk corresponds to a Rados object that we can go and get and store from the backing store. Having a shared storage system like RBD allows you to decouple your VMs from the host they're running on. So wherever the VM is running, it can go and get its disk image from the Ceph cluster. And that means that you can readily do things like live migration. The underlying object store provides the ability to do thin copies of objects. So it allows you to do very efficient clones and snapshots, and RBD exploits that. So when you do a clone of a disk image within RBD, what's actually happening is it's not having to do a whole lot of data movement or copying. It is just going to create a thin clone, and every time you touch an object within that to do a write, at that point you'll get a copy on write style behavior. The RBD client is available in several forms. So there's a user space library called librd, and that's what's used in a QEMU KVM environment to access disk images. So that requires your hypervisor to be aware of librd in order to use that. There's also a kernel module available that presents an RBD device within /dev, so code can be completely unaware that it's talking to an RBD device. It thinks it's just a normal disk. And support for RBD is built into OpenStack, CloudStack, Proxmox, and, of course, OpenNebula, which is what we care about. One last point about the way the data is laid out in RBD. The objects within a disk image end up being striped implicitly across the cluster. And that gives you very good, pardon me, this is slipping off my head again. That gives you potentially very good bandwidth across the system. If you're accessing a lot of different ranges within a disk image, those IOs will be sent to a lot of different OSDs, a lot of different network cards, a lot of different hard drives, and you can get, compared with a local drive, phenomenally good bandwidth to one of these distributed network block devices. So how do we integrate a Ceph cluster containing RBD images with OpenNebula? Well, firstly, I was trying to work out, before I came to this event, how many people would already be using Ceph. There doesn't appear to be an existing survey result for that. The closest I could find was this one that I've referred at the bottom, which tells us that it's actually a little under half of people using distributed storage at all. So right now, those would be the people who'd naturally look to use Ceph, as opposed to using one of the other open source alternatives like LusterFS or using an existing NFS filer. If you're currently using local storage, you might still want to consider using Ceph. Even if your disk images are ephemeral, you might look to get performance gains from having a high-performance distributed block device. And you might not, you might be surprised at how little overhead you'd have from having thousands of virtual machines, even if they're ephemeral disk images, because you can do thin copies of these images. There's not very much overhead to creating all those multiple copies of the disk image within Ceph. As I mentioned, librd is a user-space client library that allows access to these block devices. You have to have the right version of QEMU and KVM, or libvirt, I should say. So these are, this code is all upstream. It's all there. But if you're using one of the older enterprise Linux distributions, you might find that you need to get some third-party packages that have the support for the Ceph stuff. And most importantly, just get the most recent versions you can of these things. And within OpenNebula, the support for RBD is actually fairly lightweight. For the most part, it takes advantage of the existing support within libvirt. And that means that all that's required from the OpenNebula datastore driver is to provide the hooks for things like the creation, the copying of the block devices. And those just sit on top of the RBD command line tool that comes with Ceph and call into that. And there is lots and lots of documentation online if you want to follow up in more detail about that. So what if you're not using libvirt, QEMU volumes? Well, there are still other things you can do. I mentioned that RBD also has a kernel driver. So if you have a hypervisor which is unaware of RBD, then with a little bit of configuration, you can still point that hypervisor at your RBD devices by mapping them using the kernel module. You can also do kind of interesting things. One person yesterday mentioned that they were using Docker, and for their data volumes for Docker, they were creating RBD images and formatting them with ext. I think it was ext4, it might have been a different file system, but a local file system. Yeah, it was you, right. And using that as a way to provide data volumes. So although Ceph doesn't provide a sort of out-of-the-box Docker solution right now, it's very flexible, and you can create this type of solution. And in general, if you have something that wants to speak NFS or wants to speak iSCSI, you can layer those things on top of Ceph. So you can create an NFS share on top of CephFS. You can have an RBD volume, create a local file system, export that over NFS, or you can have an RBD volume that you've mapped somewhere and expose that using iSCSI. So there are lots and lots of different ways of doing this, although for the best sort of performance and robustness in private clouds right now, it is recommended to use the libvirt QEMU type solution unless you have a strong reason not to. So installing Ceph, configuring Ceph, that's fine. There's lots of documentation online about how to do that. But before you design a solution for your OpenNebula cloud that uses Ceph, you need to think about how many servers are you going to have, how many disks, what network, that kind of thing. And I mean, I work for a software company, so I don't make specific buy this piece of hardware type recommendations. But there are some important points to bear in mind. Because of the way Rados works, it's much better to have a large number of light nodes than it is to have a small number of heavy nodes. And that's because if you, for example, only have 3 big storage servers, if one of them fails, what Rados is going to do is try and re-replicate and recopy that data to the other 2 servers. And the ratio of the amount of data that you're moving to the amount of bandwidth that's available on your remaining servers is quite bad in that case if you've only got 3 servers. And it can cause degraded performance on your system that you might not realize until you experience that error case. Whereas if you've got 10 servers and one of them fails, that 10% overhead of moving data is much easier to deal with because it's spread over many more peers. And that can be counterintuitive if you're coming from other storage systems where you would have sort of big direct attached storage arrays and a small number of servers. With Ceph, you want a larger number of servers, a larger number of CPUs, and the ratio of CPUs to disks should be higher. OSDs use a write-ahead log, they use a journal. And one of the best ways to get performance is to add an SSD to your server and use the SSD for the journals. That will improve your latency a lot if your workloads care about latency. And in a similar way to having a larger number of smaller nodes, you also want to think about having a larger number of smaller drives. Don't go out and buy the biggest SATA drives you can afford, because if you do, your ratio of IOPS to capacity will be compromised. And you'll feel that, especially in Ceph, when you are re-replicating data after a failure. There are lots and lots of IOPS that are going to be used in that process of rebuilding and migrating data. And so you need to make sure that for every terabyte of capacity you have the right number of IOPS available by having the right number of spindles in your system. And this applies to the network as well, all the same arguments. Make sure you've got plenty of network bandwidth, ideally 10 gig. So most recently, the Ceph release cadence is quite hectic. In May, the Firefly release of Ceph added major new features, cache tiering and erasure coding. So previously, the resilience in Ceph was always provided by replication. Since Firefly, you've had the option of using erasure coding, which is a fancy name for what we would do in, for example, a RAID 5 array. So rather than having 2 or 3 copies of the data, we break the data up and encode it so that we have parity chunks to go with it. And that allows you to get much more efficient use of your underlying disks at the cost of some performance, because modifying an object within an erasure-coded pool is much more expensive when we have to read it back, modify it, and re-encode it. So that works well if you have a lot of cold data, but you don't necessarily want to use that for your hot or even your warm data. It's a trade-off. I mentioned that you can customize which on-disk backend you're using. Since Firefly, it's been possible to also use not just a local file system like XFS or ButterFS, but to use key-value stores like LevelDB and RocksDB. And that's something that not many people are doing that in production yet, but for a performance gain, it's a very interesting area, especially since some of these key-value stores are being optimized for emerging flash technologies. So if you're doing interesting stuff on SSDs, the ability to use a key-value store rather than a file system can be quite advantageous. Firefly also added the ability to manually specify among a number of copies of data which OSD should be considered the primary for reads. That means that, for example, if you have 2 storage racks and your VMs are all in closer network proximity to one rack, you can tell Ceph, I want to use the OSDs in this rack as the primaries, and all the VMs would send their reads there, and the other rack could just be used for the other copy. And that's purely a performance optimization, and the topology of your network will tell you whether that's actually useful or not, but it gives you more options. In October, the Giant release came out, and that was more of an incremental improvement. There was lots of stability, lots of performance work went into that. One notable thing for RBD is that we enabled the client-side in-memory cache by default. So RBD will now provide a write-back cache in RAM. That isn't safe to do for all virtualization technologies. It requires that the hypervisor sends flush operations so that we know when to clear the cache. So what happens is that RBD starts up by default in a write-through mode without that caching. And the moment it sees a flush from the hypervisor, it goes, right, this hypervisor supports flush, and it will automatically switch into a write-back caching mode to give you better performance. The next major release of Ceph will be Hammer. That will be coming out sometime in the spring. And I'm deliberately not making any specific commitments about what will be in that, but you can see our development plans online. All of that planning happens in the open. And look for more development on the Ceph file system in Hammer. That's something that we're working on a lot at the moment, and the file system is what I personally work on, even though it's not really what I'm here to talk about, so quite looking forward to the Hammer release. I mentioned the file system. There are other extra bits of Ceph outside the Rados RBD path. So Calamari is a graphical user interface for Ceph. It provides a fairly simple dashboard user interface that will tell you about errors and give you little graphs of performance and what you would expect from a dashboard. Ceph Deploy is an SSH-based deployment tool, which makes it very easy to run a couple of commands to say, I want an OSD here, I want a mon there. And there are also Puppet and Chef modules available for Ceph, so you can use the configuration management tools of your choice and slot Ceph into that. I always like to end these presentations by encouraging people to get involved. If you're not already evaluating Ceph for your cloud, then why? It's free. Download it. There are mailing lists, there are IRC channels, which all of the developers are hanging out on all the time. So come and talk to us. Please report bugs when you find bugs. When you find an issue, we want to know, we want to fix it. And if you want to get even more involved in the ongoing development of Ceph and getting the features that you want into Ceph, then our periodic planning meetings, our developer summits, they happen online. They are open to the community. So you can join those, you can bring ideas, blueprints, and participate in that planning and prioritization process for Ceph. Thanks very much. So the question is, what file system do we use for the local file system on the OSDs? It's customizable. The default file system and what we currently recommend for most deployments is XFS. So if you're using Ceph Deploy or any of the other default tools, it will give you an XFS file system. Yeah. Yes, at the back. I mean throughout the stack. So Firefly was a major feature release. And so the priority for Firefly was to get the new features in and get them stable. And there are lots and lots of places just in the, not so much in the design, but in the implementation of the code where there's room for improvement. So for example, I mean, one thing I personally worked on during the Giant cycle was changing how the threading works in the client for Rados. So there are parts of it that were single-threaded in Firefly and have become multi-threaded in Giant. It's many, many small things like that. So, okay, so there are three sort of tiers of releases. There are the numbered releases, which come out very regularly, every month or so. And those are for people who are involved in ongoing development primarily. So you have in general, putting your production data on those is not such a good idea, but we really do value people running those because that's how we find out about issues early on. There are the named releases, so the Firefly, the Giant, the Hammer, and those are the ones that we've put more QA into and we have greater confidence in. And so those are, in general, safe to use. And if you are, especially if you're self-supporting and you're using an entirely sort of custom stack and you're picking components, you might pick to use one of those. And then on top of that, depending on which vendor you're using and who you're buying support from, and there are multiple Linux companies that are selling support for Ceph, including us, of course, those vendors will also bless certain releases and say those are the very stable releases. So it's a little bit like a sort of Fedora, CentOS, Red Hat type thing. You can use Fedora, it works, but if you have more stability needs, then you would probably choose a more enterprisey distribution. Any more?
Can I use a volume based on LVM to an OSD as opposed to a single drive? Is that a limitation? Is that a restriction that I need to use a single drive for OSD?
So it's inconvenient to use LVM at the moment because of the way, just the implementation of the OSD code. We actually use partition IDs as a way of identifying OSDs so that the system can automatically mount what is there when it comes up. But there's nothing fundamental stopping you using LVM, but you you will find most of the tools by default don't like you using LVM. Some of the magic doesn't work if you're using LVM. You would also need a good reason to use it. So sometimes people want to aggregate a number of hard drives into one with LVM and use that as an OSD. In general, that's not a good idea because what you want to do is let Ceph manage the failure domains within the system. So if you take 10 drives and make them into one LVM volume, if one of those drives fails, you're losing an OSD. It's better to have 10 OSDs so that Ceph can dynamically move around the data in the way that it knows how to do. Yes? Mm-hmm. So currently, the situation for georeplication is it varies depending on which interface to Ceph you're using. So the most mature thing that exists at the moment is the RGW georeplication, which is the S3 compatible interface. There is, I'm not sure exactly what the status is of the work in that direction on RBD, but it's something that we're sort of pushing on at the interface layer rather than within RADOS itself. So it will, for some time, it will continue to be the case that the answer to the georeplication question is it depends exactly how you're using it. You can do a fairly efficient job of transmitting RBD diffs from one place to another if you want to do disaster recovery asynchronous replication. So there are solutions, but I wouldn't sort of make the blanket statement that georeplication all just works. It's a fairly new thing as well. Anybody else? Mm-hmm. Mm-hmm. Yes. Yeah. So the question is, what else can you do to get better performance? And it's often the case that depending on the exact hardware that's in use in a RADOS cluster, you can get better performance by modifying certain queue lengths, thread counts, journal sizes, that kind of thing. Obviously, if there was a better one-size-fits-all number for these settings, we would want to make it the default. The reason we don't publish a lot of guidance on that is just because it's so hardware dependent. What will give you the best performance? People will often find that they need to increase the default size of the OSD journals to make the most of the performance available on their systems. And you also have a lot of interesting choices about how you will break up your OSD data versus journal parts. So whether you want to use your SSDs as OSDs themselves, or whether you want to use them as journals for your spinning disk OSDs, that kind of thing. And again, it's very hardware dependent, requires benchmarking. And you were sharing some very interesting graphs with us the other day, and that's we still often see somewhat surprising results from people modifying these settings. So yes, there are a lot of things you can do to improve performance, but the onus is on the person with the hardware to try it and and let us know how it works. Yeah, absolutely. Things like FIO and that kind of thing. Yeah, using off-the-shelf benchmarks. And there are also a couple of benchmarks built into Ceph. So there is a RADOS client benchmark, which you just run by typing RADOS bench on a client, and that will allow you to test across your population of OSDs, how much bandwidth you're getting, and so on. There is also a benchmark function built into the OSDs, so you can remotely say to an OSD, please benchmark your local device. But what we all care about is the real-world performance that your applications will get. So using off-the-shelf benchmarks on the client side is always the sort of final answer to whether it's as fast as you want it to be. Yes?
Thanks for the presentation. Congrats for the product. And if you're considering to buy a new hardware, like maybe some of the people here are thinking about test Ceph with initial hardware configuration, what's about
Okay, so the questions are, should you use RAID underneath your Ceph OSDs, and what's the minimum number of nodes you can have in a proof of concepts situation? So should you use RAID? Almost always no. Much as with aggregating drives with LVM, it's something where you want to leave that to Ceph, to let Ceph do its job, and present Ceph with the most fine-grained view of your system possible to get efficient re-replication and data movement when things fail. Obviously, the motivation people have for using RAID is usually that they don't want to pay the full replication cost of something like three-way replication. So you'll have people doing two-way replication cluster-wide and then having RAID 5 volumes or something like that. There's nothing stopping you doing that, but we're not finding that most people end up sticking with that configuration. And going forward, we're going to see more around the erasure coding within Ceph. So in the long run, that sort of problem should go away. But again, try it, benchmark it, especially if you have systems that just came with RAID controllers, so you're effectively not paying for the RAID controllers, then that changes the calculus of it. Whereas if somebody was starting from scratch, and we would, I think, almost never say, go and spend $1,000 per machine on a RAID controller, because that wouldn't be good use of money. So the second question is, how small can you go? You can run a Ceph cluster on one machine, if you want to. That's what we do for software development. In practice, the smallest clusters you see are usually something like 3 mons servers, and sometimes people will go as low as having like 3 OSDs, but for something that's going to sort of faithfully represent the way a real system at scale would work, I would look to be more in the 10 range. So if you're doing proof of concepts, rather than buying a small number of new systems, sometimes it's even better to take some sort of 3-year-old hardware, if you've got more of it. So maybe they're kind of crappy servers, but you've got 20 of them. And that could be a more faithful proof of concept type thing, as long as you can put decent drives in the older machines. Yes? So the question is, what if my machines are inconsistent, some are fast and some are slow? By default, Ceph will change the balance of the data depending on the size of the OSDs. So if you have some smaller OSDs, it will automatically put less data on them. You can also change those weights by hand. So you can decrease the weights on some worse hardware. But obviously that will also mean less data is sent to them, less data is stored on them. You might get less utilization out of the drives. So in general, the simplest thing is to make sure that if you've got some slower machines, have smaller drives in the slower machines as well. Or change the ratio of OSDs to server for the ones that have the weaker CPUs. So yes, you can do it, but as I think you're probably imagining, you have to think a little bit about it to avoid imbalance there. You can also do things like if you have multiple pools. I didn't really touch on pools because we weren't at that level of detail, but if you have multiple pools in your system, then you can say, well, I'm going to put this pool on the slow OSDs and this pool on the fast OSDs and use them for different things within one cluster. That's also an option. Okay.
Thank you.